The sky above is studded with stars and countless galaxies. In them we can read not only our origin, but also our final destination. The first phase of our journey is complete. We are ready to undertake the second. With robotics, advanced technologies and sheer daring, we are now going to places that before we only dreamt we might ever reach. It was here at Peenemünde on the Baltic coast where the opening shots of the space race were fired. Not an auspicious occasion. The backdrop to this extraordinary effort was World War. The chief engineer did mutter, however, the rocket functioned perfectly, it just hit the wrong planet. Time and tide have changed that frontier. Now science and commercial imperatives lead the way. Our push into the new frontier is now genuine and humane, guided by science and the hunger for discovery. Soon it will be underpinned by the commercial realities of tourism and mining. Research and engineering advances are ongoing. New communications and sensing technologies, new space systems for advanced aerobraking, new materials and manufacturing processes for new spacecraft, and safer launch systems, all aimed squarely at a return to the moon. Then on to Mars for a long-term stay.
The human flight component would like to see an experiment where resources on the surface of Mars, from the rocks or the atmosphere, could be used to generate fuel or other parts that would enable future exploration in cutting the tie, so to speak, to Earth. So you wouldn't necessarily have to bring everything with you. You can actually manufacture it on the planet. And that's a really exciting additional component that we've been exploring and analyzing in this work.
This will extend our reach even further, with planned excursions to the asteroids and comets giving us access to even greater resources. At the same time, it would help us protect Earth from wayward objects posing a threat to our planet. Then there is the challenge of the greater solar system, visiting the outer planets and their moons. Jupiter's Europa, Callisto, Ganymede. Or Saturn's Enceladus, a potential life-harboring location. Or cloud-covered Titan, which holds vast hydrocarbon resources. Then, the great interstellar voyages to other stars and other planets. Like HD 189733b, a gas giant. Or Gliese 1214b, a water world. Or even Kepler 186f, a nearby Earth-like planet. Our first stop in this journey takes us into orbit, where we can continue to look down at the world's changing environment and study the planet we call home. We humans are mere passengers on board this vessel called Earth. We cannot control the direction she takes, how fast she spins, but we can influence her complex and dynamic ecological climate engine. To study this machine that sustains us, scientists have used satellites as one of their primary tools. Of the 6,600 satellites launched so far, some 3,600 remain in orbit, with only 1,000 still operational.
There are two main sorts of satellites that we use for weather forecasting. The first sort is the geostationary satellite. Now, these geostationary satellites are launched into orbit at 36,000 kilometers above the Earth's surface. And at this height, they orbit the Earth precisely once per day. I can illustrate it like this. The Earth rotates around its axis on a 24-hour basis, and at the same time, the satellite orbits the Earth. So it always stays over the same point of the Earth. In this way, it takes an image of the Earth now with our MSG series every 15 minutes, and it can provide very high rapid update cycles from that data. The other main sort of weather satellites we have are the polar orbiters. Now, these orbit the Earth at a much lower altitude, about 800 kilometers, and they orbit pretty much over the North and South Pole in what we call a sun-synchronous orbit. Now, because they're much lower down, they're able to provide us with a much more detailed view of the Earth and the atmosphere.
The complexity of the Earth climate model is due to a range of variable inputs, from solar radiation, solar winds, magnetic fields, gravity, thermal absorption, to water temperature and salinity, ice and cloud coverage, carbon dioxide and other trace gases in the atmosphere, to name just a few. The first order of business has been to monitor our weather. Maximum scientific value comes from long-term data gathering. It has to be reliable, continuous and uninterrupted. To this end, ESA and EUMETSAT have launched their latest satellite, METOP-B.
METOP-B is particularly important to provide continuity of this data. This data has the largest single impact into the weather forecasting system. So it's very important that we maintain this capability, and for climate purposes it's very important that we maintain a continuous record in time.
Apart from accurate weather data, it also carries a GOME, or Global Ozone Monitoring Experiment. It monitors ozone concentrations in the polar regions.
This is an instrument that measures in the ultraviolet and visible part of the spectrum to retrieve information on the ozone structure in the atmosphere, which is particularly important for understanding the recovery of the ozone hole, and also it's now used within weather forecasting itself.
Weather forecasting is important for everybody because weather impacts a large amount of society, economic aspects. It impacts everyday's life. Satellites improve weather forecasting, so improved forecasting enables us to provide earlier warnings, better warnings, give us more time to warn.
There is now a concerted and coordinated effort by the major space agencies NASA, ESA and JAXA, along with their international partners, to launch a series of next-generation Earth observation satellites, each with specific instrumentation to address the many variables making up our climate. Joint partners NASA and the Japanese Space Agency have launched an international satellite mission, GPM. The Global Precipitation Measurement Mission will set a new standard of observation of rain and snow worldwide. GPM consists of a core satellite with 8 constellation satellites. With precipitation radar and a microwave radiometer, the system will collect global data every 3 hours.
The GMI produces a critical reference standard which unifies all the member satellites of the GPM constellation. The instrument has 13 channels, and this greater sensitivity allows GPM to measure a greater variety of precipitation type and intensity. Each channel has a frequency range that can detect a different type of precipitation. Scientific algorithms then translate the GMI's brightness temperature data into more meaningful products, such as rain rates. Because GPM's coverage extends beyond the tropics, measuring storms like these in the mid and high latitudes will improve and expand the global view of precipitation.
Conducted with the National Oceanic and Atmospheric Agency and the space agencies of France, India and China, the GPM mission data will advance our understanding of the water and energy cycles and extend the use of precipitation data to directly benefit society. Two major components of Earth's climate system are the water cycle and ocean circulation. The joint US-Argentinian Aquarius Satellite de Aplicaciones Científicas mission can map the salinity or the concentration of dissolved salt at the ocean's surface. By measuring ocean salinity from space, Aquarius will provide new insights into how the massive natural exchange of fresh water between the ocean, atmosphere and sea ice influences ocean circulation, weather and climate. One of the oldest and most venerable satellite missions to date is Landsat. A NASA and US Geological Society project begun in 1972 with the launch of the first Landsat satellite, it is the longest-running contiguous Earth imaging program. The 8th of the series is currently in orbit.
It orbits over the North and South poles, taking imagery on the sunlit side of the Earth every time it passes.
The Landsat 8 satellite makes 14 orbits per day and covers the entire globe every 16 days.
The data from the Landsat data continuity mission will be the best data that have ever been collected from a Landsat satellite. With increasing population, our land use are changing at rates unprecedented in human history. To manage and cope with these changes, we need to have the observations, the information, the data that allow us to understand what's going on the surface of the Earth where most of us live.
The data collected over 40 years of the Earth's surface has created an historic archive unmatched in quality, detail and coverage.
Landsat archive that contains all the U.S.-held data from all of the Landsat satellites, and the LDCM data will become part of that archive.
The Landsat program offers, free to anyone, the longest global record of the Earth's surface, and it will continue to deliver visually stunning and scientifically valuable images of our planet. However, the Earth's surface is predominantly water. Measuring the topography of the oceans is another challenge altogether. Begun by the Topex Poseidon satellite, a joint effort of NASA and France's Centre National d'Études Spatiales, and continued by the Jason-1 satellite, their latest mission is Jason-2, continuing to provide a long-term survey of Earth's oceans. It measures changes in the height of the sea's surface. These are used to understand shifts in ocean currents as well as sea level rise, both critical parts of global climate change. The data is used around the world to improve weather, climate and ocean forecasts. Another ocean-going measurement is the speed and direction of the winds. The Sea Winds Scatterometer is a specialized microwave radar that measures near-surface wind. The scatterometer estimates wind speed and direction over the Earth's oceans at 10 meters above the surface of the water. The instrument collects data over ocean, land and ice in a continuous 1,800-kilometer wide band, making approximately 400,000 measurements and covering 90% of Earth's surface in one day. Earlier satellites could only image the uppermost layers of clouds. CloudSat was among the first satellites to study clouds on a global basis. It looked at their structure, composition and effects. The key observations are the vertical profiles of cloud liquid water and ice water contents and related cloud physical and radiative properties. CloudSat flies in tight formation with the Calypso satellite, carrying a backscattering LIDAR, and these two satellites follow behind the Aqua satellite in a somewhat looser formation.
When we started with airs on Aqua, we had two goals defined to us, before the mission started. One, provide data to the nation's weather forecasting center, which is NOAA, and improve weather forecasting. So that was the first goal achieved, and we, the science team, felt good. The second goal was improve our understanding of the climate system, the water vapor. That is the main mechanism by which weather and climate is formed here on Earth.
The combination of data from the three satellites provides a rich source of information that can be used to assess the role of clouds in both weather and climate. The European Space Agency's Earth Explorer program has seen several high-tech satellites play their part in our understanding of the global climate.
We have launched 3 missions, meanwhile, with fantastic results and very innovative technology.
SMOS, the Soil Moisture and Salinity satellite, observed soil moisture over the land and salinity in the oceans. Cryosat, the ice mission, measured the thickness of the massive ice sheets over Greenland and Antarctica and the marine ice in the Arctic. It used a sophisticated stereo radar system and has helped give us a better understanding of the relationship between ice and global warming. GOCHE measured Earth's gravity field with unprecedented accuracy. A geoid model is crucial for deriving accurate measurements of ocean circulation and sea level change, both of which are affected by climate change. This data revealed the Earth to be lumpy and quite variable across the planet. It has led to a new map of the boundary between the Earth's crust and mantle. Another piece in the climate puzzle, and a critical one, is the Earth's magnetic field.
The Earth magnetic field is our lifesaver. There's no doubt about this. This shield is basically protecting us from the harmful effect of the solar wind, these high energy particles that the sun is constantly bombarding us with, and this shield is really essential for us and for our protection. The main magnetic field of the Earth is changing in time, and it is weakening by a factor of, let's say, 10–15% or so over the last 200 years. And what's actually going on in the outer core of the planet is what we really try to find out. The magnetometer package on board Swarm, it measures the magnitude and also the direction of the Earth magnetic field. And it does so in 2 locations. One, it has an instrument at the tip of the boom and also another instrument halfway down the boom. And together, they give all this precise information that we needed to decipher the secrets of the Earth magnetic field.
ESA is now developing a new family of missions called Sentinels as part of their Copernicus program.
It is not sufficient to monitor the evolution of the ice cap or to monitor the sea level rise during 5 years and then stop. We really need to monitor those things over a very long time period. And this is what Copernicus will bring. It will bring a long-term frame for continuous monitoring of our environment.
Sentinel-1A is the first of a 2-satellite mission that will scan land and oceans using advanced radar to deliver imagery regardless of weather.
Copernicus is the most ambitious Earth observation program to date. The European Space Agency is putting together 6 families of Sentinels that will take care of the objectives of the Copernicus program. monitoring the land, the marine environment, the atmosphere, climate change, and providing a fast response to security and emergencies.
In total, there will be 6 Sentinel missions, each pair of satellites devoted to specific observations.
Each Sentinel has a specific duty. Sentinel-1 is more specifically tailored to emergency response. Sentinel-2 is focused on monitoring of the land. Sentinel-3, together with Sentinel-6, is focused on the monitoring of the ocean and waters. Sentinel-4, together with Sentinel-5, is specially tailored to the monitoring of the atmosphere.
The International Space Station is also host to several climate sensors. Currently, the CATS, or Cloud Aerosol Transport System, is mounted on the Japanese experiment module. Using light detection and a ranging LIDAR system, it detects and measures pollution, dust, smoke and other aerosols in the atmosphere. NASA will be installing another instrument, the RapidScat, onto the end of the station's Columbus module this year. It will measure ocean surface wind speed and direction and help improve forecasting and hurricane warnings. The Orbiting Carbon Observatory was NASA's first satellite dedicated to the tracking of carbon in the atmosphere, how it is reabsorbed into the biomass, and where. Unfortunately, a launch failure has caused a reschedule of the project.
But we need the measurements that spacecraft like OCL will make in order to understand the processes controlling the rate of buildup of carbon dioxide in our atmosphere so that we can understand how it will change in the future.
Other projects in motion include the Atmospheric Dynamics mission Aeolus with its high-power UV laser, which will measure wind speed, air moisture and dust particles to advance our understanding of atmospheric dynamics. EarthCare will study how the Earth reflects and traps heat. Biomass will study the state of the Earth's forests. NASA's Clario satellite will measure incident solar irradiance and the Earth energy budget. SMAP, the Soil Moisture Active Passive, is an Earth satellite mission designed to measure and map Earth's soil moisture and freeze-thaw state to better understand terrestrial water, carbon and energy cycles. The suite of satellites now in orbit and planned for the near future will be able to peer beneath the clouds, vegetation and other surface features, monitor water salinity, temperature and energy fluxes, chart ocean currents and the change in ice caps. All this data is helping to improve our understanding of climate change and also helping in a practical sense, with flood and drought monitoring, hurricane and cyclone warnings, understanding changes in water availability, food production, and the other societal impacts of climate change.